Good morning, everyone. Welcome to today's session, In-Rail XM Edition Tunneling. I'm your instructor today, and this is David Fagerman with Bentley. And before we get going on this, I'd like to welcome all of our friends from around the world to the session, and specifically to let you know this was a special request class by several organizations around the country, in the U.S. at least. And we've got several on, and we'd like to welcome you all to this session. I hope you can hear me. I know you're in conference rooms and all that, and just turn it up. At the end, we'll have Q&A and be happy to answer any questions you may have. So welcome to today's session. To begin with, we'll go over today's agenda. First, we're going to just generally go over a tunnel workflow and what makes tunneling different than roadway design and all that. And as several of you had indicated, you wanted to be able to, combine line of sight with tunneling so you can see where people can see where entrances are and exits are relative to line of sight and buildings, and then combine this tunneling technique so that you can have good, safe tunnels. So we're going to go over the workflow. Then we're going to begin with an existing tunnel surface, get a feel for the difference between a tunnel surface and a normal topography. Then we'll look at horizontal and vertical alignments, and I must state that this is an advanced type class. Assumptions are made that you do know horizontal and vertical alignments and surfaces as we go. So we're going to look at design horizontal and vertical. Then we'll look at design tunnel sections. If you've never looked at the tunnel software, this is unlike the roadway designer or anything else. There are special sections that can be designed for tunnels. And I'd ask all of you to keep an open mind as you see this, because the application does not have to apply just to tunnels. It could be trenches, it could be any enclosed type thing, anything that has overlapping Z even, these techniques would work with. So they're not just tunnel related, but in this presentation they'll be for tunnels. Next we'll look at the actual process. And what we do is we flatten the existing tunnel surface. We'll run through how that works, how we go from real world coordinates to a custom coordinate system, and that's how we go back and forth so easily. Next we'll look at the create tunnel cross sections, and these are a little bit different than normal cross sections. You'll see how that works. Then we'll take a look at surface depressions, how those are affecting tunnels, where we can see where we need to fill or mill. We'll look at annotating these sections for min and max, and then we'll locate critical points going from a relative coordinate system back to a real world coordinate system. What you're going to see today is a lot of the behind the scenes things happening that transform from real world coordinates to relative coordinates, back to real world, back to relative, back and forth. And this is how we handle all this overlapping Z. Right? The tunnel workflow, let's look at our givens. First off, we'd have an existing tunnel surface that has overlapping Z values. So this is going to be a LiDAR type surface, a Cyrex, whatever type, generally terrestrial data collection, or it could be aerial if you ran a helicopter through a big cave even. These values need to be and have to be random points. So we have a random point tunnel, we have a design horizontal and vertical, design proposed sections, and station limits, very similar to the roadway designer, where we know what proposed sections to use. And then we also know tolerances as we get going here. What's the mill and fill tolerance values? So when it comes time to mark the cave or the tunnel, we know how to mark it so we can get the appropriate work done on it before a sleeve is put in or whatever in the tunnel. Right? The tunnel workflow continued. Now here is the requirements. First requirement, want to be able to determine a cut or fill difference between an existing tunnel surface and a designed tunnel surface. Again, I'll step back to roadway designer. Those that do roads, you can have an as-built survey and then you have your design corridor, and you can easily do diffs on that. Well, the thing with this is this thing wraps around, so you don't have that ability because of the overlapping Z. but you will have that ability after you see this. We'll look at how you can determine volumes between an existing tunnel section and a design tunnel section. Then we'll look at how you can identify critical fill or mill areas, and then generate reports so you can go in the field and do actual stakeout on the tunnel ceilings, tunnel floors, tunnel walls, where things need to happen. So these are the things that we're going to pursue accomplishing in this session. And that needs to be real clear so you know where I'm coming from here as we move forward. With the existing tunnel surface, first off, we're going to come in with a point cloud generated or Cyrex generated model loaded up. And you could load this via ASCII or an already populated DTM, or graphics, any one of these methods. And you do not have to triangulate this surface, however you can. That's the beauty of this command. You can have multiple million points but not have to triangulate, so you don't have to carry that weight around. It does not require it. Now, another thing about the existing tunnel, the XYZ values for points in the tunnel have real-world coordinates. So even though they're overlapping or whatever, if you go out in the tunnel and you want to go to an XYZ point, that will be the real-world coordinate. And surfaces will have overlapping Z values or points. We know that. And that's where Delaunay's criteria for triangulation cannot apply with the overlapping Z value points, because you could have a ceiling point and a floor point, and based on Delaunay, which says any points inside this triangle, I mean, you form a triangle and you can't have points within it. So if we had ceiling points, they would automatically connect to floor points and our models would be all messed up. So right off the bat, we have the criteria that Delaunay does not apply here. All right, let's step over for a moment. And I'm running InRail XM Edition, latest service pack on MicroStation XM. Okay, I've absolutely got nothing loaded at the moment. I wanted to start from scratch, let you see where we're coming from. And what I'm going to do is simply come over here for a moment to geometry, and I've got a geometry file loaded, and I'll flip it over to this so you can see it happen. Those of you not familiar with this, oh, excuse me, let me flip over to Explorer. All right, and then here we'll grab an alignment. All we'll do is drag and drop it, and it will load it up. And I didn't have to flip to that. In fact, I'm not going to flip to surface, but I'm going to go to surface, and I'm going to grab another alignment, or I'm sorry, DTM, drop it there. It's loading it up, and when I go to surface over here, it's there. Okay? So from Explorer, I just dragged and dropped. And we'll take a look over here. If I look at the model, I've got almost 500,000 points in here. And if I flip over and look at the elevation range, my elevation minimum is, we'll see it here in a moment, an 804 low and an 813 high. So those are real world coordinates directly. And if I look at my northing, I've got 151,000, and my easting, we're looking at about 616,000. Those are real world XYZs. Now that's how it comes in. When we move forward, we're going to work in a relative system, and I'll explain that as we go. Just for a moment, I'm going to show the surface, and this is a large one, so I'll have to wait for a moment just for the display updates. But I'm going to come over here, and I don't have this triangulated. So if I went to perimeter and went apply, no triangle found. Okay, that's fine. You don't need it triangulated. I wanted you to see that. It can be, but it doesn't have to be. I'm going to go over here and view surface features instead. And everything's under random points, so I'm going to apply. This will take a moment. We'll give it a moment to display. As this data is coming, this is the real scan data coming out. And we'll have that in a moment. All right. Just about there. Like I said, this is 500,000 points that we just displayed. Close that, and we'll fit this. and I'll let the display catch up. So what you see, this is a top view of this, all right? And let me just zoom in a moment here. I'll zoom in on this a little bit. And what you see in a moment here will be the point clouds that were gathered in this area. So I'm going to come up to my view for a moment, and I'm going to just flip this up. Hold it down, and I'll flip it to a front view. And there you can see, looking inside the tunnel, and we can see all the undulations and everything. And this is a for real thing. So in 3D space, now if you received from your client a vectored survey, and in this instance it's from again from terrestrial LiDAR Cyrex type data collection. But even if you had total station data that you shot with random points like this, you could bring that in. So here we're looking at it, and you're seeing the tunnel as it is in 3D space. So this thing, if I just do a quick check on elevation or coordinate, I can see I've got the 616 and 151,000 and the 809 elevation. That's exactly what I expected. Okay, so let's flip back up here to top view, and I'll fit that out. And what I want to see now is where is the alignment relative to this. And when we do that, I'm going to come in here, and I've got a center line alignment defined. And let me tell you something now. This, and I'll display it, and then I'll explain it. View it. It'll come. There you see it showing up right through here. And let's go to Tools, Tracking for a moment. We'll go to Tracking, Horizontal, and let's see which direction this thing is going. So we'll come in here, and we can see our station 21. If you look at the bottom of your screen, 21 plus 7, 81. And as we come down this way, 21 plus 8, 17. So it's going from top to bottom on stationing. Okay? So it's north to south is increasing stationing. And notice that this tunnel is running right through the area on this alignment. I'm going to do a fit now, and what you'll see, this is realistic. That tunnel is just a little piece of a great big long corridor. Okay? So everything you normally do with inroads, you do with this. You collect your data and all that. It's just that this also zooms in. I mean, it's going to work right in this particular area. Let me delete the alignment, and then we can see right in here is where the surface is, and I'll fit it back here. There it is. Okay? So this is the surface we'll work with. We've just looked at where the alignment is that runs through it, and I'll put that back right there. You can see where the alignment is. We want to take this data, and we want to now apply a typical section to it and be able to tell if we have to mill or fill. Okay? To our existing tunnel for a moment, and I'm going to step forward, and we're going to discuss the next step for a moment. And the next step is the horizontal and the vertical alignment. The horizontal alignment is a, as we've seen, a known horizontal control line through the tunnel. It can have tangents, circular, spirals, anything. Anything that you do with normal geometry, you can have. The vertical is the actual profile grade line of the known control line through the tunnel. And what this is when we attach our typical section, very much like Roadway Designer, that's that 0 point, 0 offset. Okay, so this is the horizontal and vertical, very straightforward, and they are based on real-world coordinates at this stage. And the combination of the horizontal and the vertical defines the XYZ path for the proposed design tunnel section. So as they run down it, it's just like the Roadway Designer, it builds a corridor essentially, but a little bit different. And let's step over for a moment to our geometry. And what I'm going to do just for a minute is look here. I've got a horizontal and a vertical. If I review this geometry and I've got it set to alignment, we can see we've got a tangent, we've got clothoid, we've got linear. I mean, we've got all kinds of things on this. It's a very big alignment. And a keynote here is that it starts at 13,581, and then when we come down to the bottom, it ends at 33,999.96. Now, first off, I don't need to carry all this alignment with me as we move forward. All I really care about is the stuff in the tunnel, all right? That's all I care about, so I don't need to bring all this with me. And I'm going to make a decision as we go just to chop off a piece of this as we do our workflow here. Okay, let me close that. Now, the other thing is, notice here on the vertical, I'll do a review of this. We have a true vertical alignment. Okay, so these elevations are real grade, but these are the bottom of the tunnel. So these are the bottom, and remember, we've got stuff that comes up on top of them several meters above it. So you can see the grades as it comes in, and it's just your standard design grades, all right? So you design it how you want it. In fact, as we do this, I want to say this: you can step back just like you do on a corridor design with a roadway and modify your verticals and regenerate these sections. So this is an interactive tool. I'm going to just take you through the workflow though. So this vertical goes hand in hand with things. One thing is key to tunnels. Those of you that have ever run the bridge application is somewhat similar in that we recognize parent-child somewhat relationships between an alignment and girders and diaphragms and all that. On the tunnel, we take this horizontal name information right here, and you're going to see that name appear in surfaces that we create. That is the link that moves things back and forth between the new coordinate systems that you're soon going to experience. All right? Right. Let's go back to the next step here. We've looked at a horizontal and vertical, and I think that's real clear to all of you. You all know what that is. Like I said, it's an advanced class. But now, maybe none of you have seen this piece right here. This is the uniqueness to tunneling. Number one, the design tunnel sections tied to the horizontal and vertical alignment at the zero offset point. Okay. Number two, we've got a section data file in the product directory under data, metric, tunnels, and it's called tunnel sections. And I'm going to go into that in a moment and show you what it does. But this is the simple format of this, and it's very well defined, so you don't need to take notes or anything. It's all in there in the document. But you have a name, like this is the name, kind of like even in Rail where it pops up turnout names. This is a section name for a tunnel. Description, in this instance it doesn't have one, it could. Then it works with a begin data. What this is, zero means begin at, like I told you, that profile grade line at center line, okay? And then it does the offset 1.07. So there we've got that, and then this is the end offset on the other side, or delta elevation, I'm sorry, right there. So this is a tangent, begin, end. This is a circular element. Begin, center of circular element, end of circular element. In other words, PC, radius point, PT, and there's a radius. You can say that's a very small radius. But what this is as we go forward, I'll point this out. As we get into sharp PIs with acute angles on a tunnel, to avoid overlap or voids, you put a small radius in, and then you'll avoid a void. Okay? And then so what you really are looking at here, this is a tunnel section, just like a road section. Here's a piece of tangent. Here's a circular, 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 circular. And notice 231, these numbers right here as they move forward, or I'm sorry, this one, that number is that number. That number is that number. In other words, the PT and the PC, it's a compound curve actually. They move forward with differing radii. So all of these through here are circular curves. This is a tangent, and it comes back to the 0 point, and that's the end of the section. All right, let's look over here in this product directory data metric tunnels section. This is the key to tunnels, and when we start running it, you see it's very easy to run, or pretty easy. All right, I'm going to step over here to the product directory, and I've got it program files, Bentley, and we'll come down here to inroads 8.9, data metric. And in the data metric folder, we'll come down and look for a tunnel. But this is simply a text file, And remember I said that you could pick this up easy and work with it. I'm going to open this up for a moment. All right, what you see here now is the tunnel information, and this goes through exactly the format of the data, what the data is, and it's very it explains things very well, so you know how to define these yourself, and you could pick this up and run it very easily. And this is really neat because this will do things you can't even do in a Delaunay based model. So this is a very neat tool. Okay, so that tunnel sections text is a key file to just be aware of. I'm just pointing that out to you. Okay, so we've looked at that. We've got a typical section here. We know how we define it. So when I come up and start using it, it'll make sense to you. Let's step into the actual tunneling process. If we want to utilize existing tunnel surface, this is what we want to utilize. We want to utilize existing horizontal and vertical geometry and station ranges for design sections. So, I mean, the same thing again that you do on a road. You've got your existing surface, your existing geometry that you want to use or proposed, and then you know the ranges that you want to run sections on. All of that's in real world coordinates. The resulting things down here are going to be all transformed to a relative coordinate system. Now here we're going to generate a special horizontal alignment for the tunnel itself. This will have the same start and end stations as the original horizontal alignment and vertical. However, it will not be true coordinates. The coordinates will not be the same. It's used just as a reference line as we unfold this thing. The differences surface will represent an isopack between the existing tunnel surface and the design sections. And in other words, what's going on right here is we're taking these design sections and basically like running the model. We're running the model. We're taking the profile grade line, the horizontal alignment, and the typical section, and we're generating what that model would look like, that true design model in 3D space. And then we compare that with the field survey point data. Okay, that's how we're getting this different surface. And what happens is all of this will roll over and triangularization will take place as we generate this with this flatten command. And lastly, there's a zero surface which represents the design surface, because the design surface from the typical sections, that is actually where zero was at. I mean, if the existing survey matched that exactly, our different surface would be all zero. But it won't be, because it'll be above or below it generally. But we use this so we can generate cross sections and run volumes and things like that. So let's step over now to the tunneling, flattened tunnel surface. Okay, and what I've got right now is the tunneling commands turned on. We'll see that here in a moment. And if I hover over them, I've got flatten surface transformation. Next one is create tunnel cross sections. Then surface depression check, cross section minimums and maximums, and lastly create critical point report. And let me just try to overview it for a second, make it clear. We're going to start over here, drop all this stuff in a flattened coordinate system so we can work with it, because we can't work with this wraparound stuff. Then we're going to come over here and generate tunnel sections so we can look at it graphically. And if we need to modify our design, we've got that graphics we can look at, and we'll come back, and just like we do road sections and we go back and forth with sections, we do the same thing with tunnels. Okay? Then we come over here, we're going to, after we've run this back and forth, iterative process potentially based on sleeves in your tunnel, then we come over here and we run what's called a depression check. And this is where we can come in, and based on the design and the best fit, really design build, then we say, okay, we need to fix these areas and we want to find them quickly. These are the mill and fill. We can annotate these in a normal cross section, and then when it's all said and done and we want to go stake it out, that's that create critical point report. So we can upload that on a total station. Probably GPS underground isn't working too good in this, So it would be total station or some device similar to that. And that would be the true XYZs. All right, I'm going to start out over here on the left and make one other note. We only have one horizontal alignment right now, and those are, it's got real geometry behind it. We only have one at the moment. When I bring up the flattened surface transformation, we're going to start out here with the original surface being tunnel points. That was the LiDAR surface. Of course, it can be named anything you'd like. Here's my geometry project. Here's my horizontal and my vertical, which we've already talked about. Simple corridor layout. Now, the one thing I want to do right here is start it. I want to start about in here. I don't need to run this whole gigantic corridor. So I'm going to do a start station. All I'm going to do is come over here for a moment, and I'm going to go to tracking horizontal, and I'm going to come over and touch here, and I see 21 plus 781, and that'll be good for start. 21, 781, tab. And then I want to come down and check down here, and I've got 21, 820 looks good, 21, 820. Okay, so I've got my start and end. Let me explain something. These are going to be the begin and end stations of our new coordinate system as I move forward. I have a start section, and this is from that ASCII file, that tunnelsection.txt, and I can pick any one I want. And what it is, they're just typical sections that have different radii, things like that. Now, if I use a stop section that's other like this, and I execute, there's straight line interpolation between the tunnel sections as we go down based on our settings through here. But I'm gonna just run this thing as one typical. And horizontal, to make it real simple for you, just to try to remember this, I'm going to call this baseline. And when you really use this in practice, you're probably going to want to reference it, to this horizontal alignment, maybe by some stationing, stuff like that. Different surface, I'm going to just, so it's clear as we move forward and you don't forget where it came from, I'll just call it difference. And zero surface, I'll call it 0. Okay. Now let me explain something. When I execute this, we will take these values here as our typical, this station range, that horizontal and vertical, and build from up here a design or proposed typical surface. We will then take the original surface, which is tunnel points, that will be flattened down, because not even triangulated or triangularized yet. It will be flattened down and then compared against the tunnel design surface. And the comparison between the walls of the design and the tunnel points, they'll be projected in orthogonally. And basically behind the scenes, we're using the same principle as the clearance report. Horizontal geometry clearance report, that if you're in a circular, you go orthogonal to the circular. That provides the station and the offset. It's the same concept, except it's running in 3D space. Really neat, actually. Okay, so here we'll build our design surface, and at the same time we're going to build this baseline that uses that begin and that end station, create this different surface that compares the models, and create a zero surface. It will have zero elevation, but it will bound the different surface, so we can automatically use it for volumes or isopacks or anything else. So all I have to do at that time is apply, and this is 500,000 points, and it will run quite rapidly. So you get an idea here. This command will grab enormous data and run it very rapidly. So we can see over here loading up. We're going to triangularize in a moment as it steps past the feature building. And see, this is like running Rollway Modeler. Remember that. Or Rollway Designer. Now it's triangularizing, and it comes back. And so what we've just done is created this baseline alignment and a different surface and the zero. And over here, here's baseline, all right? If I look at that, it took along the vertical with it too, from up here, the same vertical. But let's review the horizontal for a moment. Remember what I told you about stationing. As we come up here in the view, we can see 21781 is the begin station, and that's also the dummy begin easting. because we generate a line that's due east, and this happens to be 39 meters long, so 21,820 is the end, and the northing is 0. So you can see we've got this dummy baseline. It's not even close to the coordinates of this system, okay? And it's the Versuch Mitholz on this. So those of you that recognize what that means, that's a good thing to know. All right, so we've got this baseline. Notice the description. I want to make this clear to you. See this right here? This is our linkage. I didn't put that description in. It did it when it executed. That is the same as that, right? And that's our linkage as we go from a relative coordinate system to a real world coordinate system. And this is the really neat stuff that happens, like I said, on the fly. Okay, we've got that. Let's look over here to surface for a minute. We've got a different surface. And let me expand this. The different surface has 415,000 points. And if I look at the coordinates, though, northing, easting, elevation, that stuff, that coincides with the same principle of the coordinates of the baseline. So it's matching in that vein. Here we go. Maximum easting, 21,819, which coincides with the stationing. Okay? So you can see that, and you can see the elevation deltas, very small. That's the difference between the design and the original. And this could have been totally off the typical sections. So we can see the numbers are a different type of number. And then if I look at 0, those will just be the bounding points, range points, and those should have all elevation. Well, it's got a 10. I've got some range point in there at 10. That's what that is. But the true elevations are all 0. So that's fine, the random. All right, so we've got that. We've generated a different surface and a 0 surface. At this point, we've got this, and we can come and take a look at it. Now, in fact, I'll do that. I'll come over and I'll go View Surface, Perimeter. And remember, these are triangularized so we can see them. I'll go 0 first. That's yellow. And then I'll put the difference out, and I'll make that red. And then we'll do a fit, and it'll take us quite a long ways away. Okay, see the big separation? That's okay. That's what we expect. And you've got two options. One is you can delete the graphics over here, which I'm going to, because this is such a small thing down here. I'm going to just zoom out a little bit, and I'm going to simply come over here and use my selector and delete graphics. Give it a moment to catch up on all sides. A lot of graphics. That surface was huge, graphics wise. We'll be here in a moment. And as soon as we delete this, and this might take a moment, there we go. One thing I like doing when I'm working with these bigger LiDAR surfaces is I will compress them. So we'll compress the model for a moment. Okay, and let's come back one more time and we'll view our perimeters. There's difference, that's red. Let's fit it. And we'll come over here on 0 and we'll make that yellow. Okay, so you can get the feel right here. And what I'm going to do just for a moment is come over with a fence. I've got a little fence right there, and I'm going to go Surface View, Triangles, and I'll take the difference inside, and we'll just take a quick look at this. It's a lot of points, that's why I didn't do the whole model. And there, when we come in, we can see this. I'll give the view a second to catch up. This is a different surface. This compares the design to the existing tunnel. All right, and it'll catch up here in a moment. You can see it's very dense, and I know this will take a moment too, but I'm going to do it. I'll flip it into ISO, and you'll see in a moment here the undulations, but these are not surface undulations, these are delta elevation undulations. In other words, if everything was at elevation 0, then we would have no milling and filling. But if it's high or low, then we have the cut or the fill scenario. Okay? So let me put that back to top, but that gives you a little bit of a look at what's going on. And I'll fit this back. So we've got that right there, and we've got a baseline running along here. If I come over here now, back to geometry, and this baseline's active. If I come over here and I go Tools, Tracking, Horizontal, as I come through here, notice the station, I'll start here, is about 2179. I gotta remember which way we're going. Yeah, 21,797 over here. Oh, I used a fence. It's my fault. I forgot. 21,781's right there. And if I go to the far side, 21,820's over here. Okay? So all of this stuff is a relative coordinate system, very similar to cross sections or profiles that are relative coordinate systems. But this stuff is tied to real world coordinates. That's the really neat part. If I come over here to surface now for a moment and I look at difference and I do a properties on it, notice right here there's that description tie. Well, wait for it to catch up a moment. But the description ties me back to that horizontal combination, and then that will therefore convert these coordinates, these low elevations, back to real world coordinates. That's what's really neat. So we've built our relationships now. We can see what's going on here a little bit. And at this time, if I wanted to, I could isopack the models or anything. Standard inroad stuff. I'm not going to do that. I'm just targeting tunneling methods right now. Back up, and I'm running through the flattening. We've just covered how we run this. We've built the models that we're going to use. Just that simple, very simple. Now you're going to see how we've got the different surface and the results, how we can create these special tunnel surfaces. Okay, in other words, let me say this, we just ran the typical road design of the tunnel. You didn't even see it happen. It just, boom, it's done. So we're going to use a different surface in the results of the horizontal baseline we just did. And this is very similar to regular cross-section methods, but in the command we're going to use right now, we have a special tunnel tab, and this is to define grid lines above or below the tunnel surface. And what we found out as we were deploying this is different than what we normally do with cross-sections, and it was the customers wanted to be able to see above or below the tunnel line different variations, or like contours, like 0.2 meter increments above it. So like if there was an electric fence running along the ground, for those of my friends that are on the line on that, and you have a certain tolerance you can get with your tunnel before you start getting shocked, you can display these lines, and then you can vary, if you have to have rubber gloves on working that area or whatever, because you'll be able to set these special control lines out there. So we'll look at how that works right now. So right here we're going to come in and we're going to use general. We'll use the baseline. We'll set an interval of a 0.5 meter, 30 foot left, 30 foot right. This is all things you're used to. Different surface, the one we just did. The source will be the baseline, not that one right there, because if I flip to that other geometry, we wouldn't have anything in the sections, not with a different surface. We'll look down at control. I'm going to run this via a controlled series or stations, and this could be whatever you want, but this matches the baseline. So go from 21,781 to 21,820. Okay, and we'll look at critical sections. Everything's good there. I will put on a planimetric line so you can see where it generates it. And the layout's good. The axes, you can set those up just like you do cross sections. Now the one difference is down here on tunnels, major grid spacing. And let's say you have a high voltage kV line, like I said, and at every 0.2 of a meter you get more and more voltage as it goes through the ground. Okay? I mean, it can be any criteria, obviously. Whatever criteria you want, you set that grid spacing. Then you can say, give me, in other words, I can take up to 5 lines of this. By the time I get to the 5th line, probably get killed, so I can't go over that. So if we go past that, that's the kill point. And up to that, I could have adequate rubber on or whatever so I don't get electrocuted. But this is where you really could differentiate these things. So we're going to set 5 lines above the design, and below it we're not really worried about that. This is undercut. If you had something inside that you had to undercut and worry about, you can put a grid there. And then minor grids per major, that's simply where if you wanted to have sub-grids of this 0.2. So we'll just take that as it is, and we've got different symbology set up as we generate it, so we're really set to go. We'll simply hit apply, just like cross sections, data button, right there. Now I just executed, and what we have to begin with is, notice here the stations as it walks down it, because this is an overlapping type of section, which let me show them to you first. Let's come into one. You see right here as this goes around, let me give it a moment to catch up. This blue line right here, that line right there is the design surface. In fact, I'm going to zoom way in for a moment. That is the design, original tunnel design that you'll see here in a moment, right there. That is the tunnel points that we started with, that were non-triangularized, that we made into a different surface. Now what just happened right here is we actually went from a relative coordinate system back to a real world coordinate system, because that's a real Z. That Z is correct. The station and offsets are correct. Okay? So see, we're going back and forth on the fly. So here's the design section, here's existing, and these are those 2/10 of a meter deltas going through here. 2/10 of a meter between each one of these that we set up on purpose. So we've got 2/10 right there, and that'd be a 1/10 to the minor. And so what this is like I said, if you've got high voltage lines here, and as you come around, and let me move this up a moment, we'll find a spot like right here. Here's the tunnel. Like on the edges, it may not matter. The only issue may be is unless there's side cabling around here, which there could be. If there was side cabling, you could see in here, you know, you could wear rubber gloves where you get up to here, you might just about get killed. So this is very handy for marking that type of information. At the same time, the area above, and the volumes now are not based on these lines here. These are for visualization and zone clarification, so you can see where the zones are. The volumes, on the other hand, go from the design surface here to the existing, right there. And all that is summed up right here in this report, per station. This is what's really unique to the in-rail tunneling, is that it's going along, and let me just blow that up for a moment. And what you see right here, we're going down the tunnel, and you can see at the half-meter interval that I set, it computes the square meters and the cubic meters of mill or fill. So it's really neat what's going on. We're doing this, combining all these weaving in and out type things, and ending up at the end with a summation, okay, which you see here in a second. So there's the total area that has an issue, and that's the cubic meters involved of material. So that gives you immediate feedback. And let me flip over here for a moment to the cross-section viewer. Let's run this thing at a 1 and a 0.2, and we'll run these real quick, and we'll see real. I probably shouldn't have done that on the live meeting, but it'll catch up. Hopefully you can see the ground moving in it. And see, now let me say this, as we look at this, if our vertical or horizontal design is wrong, we can come back and tweak that. And what would we do? We'd go back to the very first command, flatten surface, re-execute and regenerate a new diff that would be based on the new location of the new typicals. And then we regenerate these sections. So you can optimize your design with this thing. It's really neat. It's a back and forth, and it lets you do that. So there's where your tunnel section comes across. We've looked at the create tunnel section. Now we're going over to the next item, which is surface depression check. This uses that different surface, and it does a depression check comparing vectors between points that are in the surface, and based on the equation, ratio shouldn't be ration. It could be ration, no. Depends on which facility you're in. You can take the ration equals D over L, where D is the depth and L is the length. And so what's really going on here, we're looking at a maximum depression ratio. So if we have a vector that's too much delta between points, then we can flag it and do something about it in a tunnel. So if you have, like a really jagged edge or anything, it will all be flagged with depression check. Now the gap check is another thing, where if we had something blocking us where we couldn't get points in the surface, the gap check will go out and find it and flag us that, hey, don't think this is good, you need to go back and get more data, or don't make a statement here, do it in the field. And then the results are the depression surface, and the Z value for this is the ratio or ration based value for the Z. So the Z value is not a true Z, but the bigger it gets is the worse the ratio. So you could use that. And again, this comes down to people doing tunnels. They use different criteria than people doing roads on how they evaluate. And then difference elevation is based on the value for the Z. This is looking at the differences. And then that gap surface that we can create just shows us where the gaps are. So let's run that for a moment. We'll come over here now, and we're going to come over to depression. Surface depression check. And here we'll run that against differences. And here, by default, we're set up this way, and the help is very good on this. But here's the max length, and here's the minimum length, and there's the delta depression ratio, the D over L. So we can take that and then check at this interval and iterate as we go through, save boundaries, and here we're going to call this depression. And that'll be a special surface in this relative coordinate system that shows us these ratio values for Z. And correction will be a correction surface. And what that is simply coming in and telling us how much cut or fill is being applied here. And that can be tweaked. Now, so I've got that. If I turn gap check on, then we would have that, but I'm not going to do it. I want to run it this way right here. So I take the differences, I apply this criteria to check for depressions, and when I apply, it runs very rapidly on those 500,000 points. So if I come over here for a moment and look at surfaces now, here's correction, and let's look at correction. It's got 2643 points that had an issue. And when I look at the elevation ranges, here they are. And really, that's, I think that was a range point, the bottom one. That disregard the 10. But this 0.35 is the high number on the correction. Let's look at a depression. At the depression randoms, we've got a 0.76. That's a ratio, 0.76. So if you want to look at your tunnel based on a ratio, then you'd use that number. Okay? Very simple. And these are all in relative coordinate systems. All right? Very quickly, we did the depression check. You all saw how that worked. It's a handy tool to find problems. The next thing, and I'm not going to run through it. Well, I'll try to run a real quick set of this, is the annotate of local minimum and maximum on either side of a zero surface line. And this is used for just in a flat section looking at a design tunnel, how it's laid out. Just another way for you to look at it. So let's flip back here for a moment and see how these have all been laid out, and those have been projected back to real world Z-type values. I'll give this a moment to catch up. Now when I use this command, I have to do it a little bit different. I use the standard cross-sectioning. So I'll go to cross-sections, create sections. And when I get in here, I'll still use the baseline. And this time I'm going to use the different surface and the zero surface. And I'll pop that zero to a different color. Cross-section line. We'll make that red. Okay. And apply it and close it. Well, I'm sorry, I did them both. I didn't have a different feature, my fault. But that's all right. We'll run that. We'll look at the source is the baseline. And one thing down on controls, we'll run it through that range, and we're good with that. Let's just run a simple cross-section set. And let's look at that for a moment. Under cross-section viewer, we'll flip to that set, and we'll step in here, and notice what you'll see here. This is the zero line. See, that's zero elevation right through here, and that's the differences above it. So as I step down it, if I actually run this thing, we'll run it quick. You'll see them flashing in front of you, and this is where we come above or below our design tunnel. So as it steps through, if it goes above or below, wherever it crosses the zero line, then we can have a min or a max elevation. So let me step back here a minute. Let me find one that's got a little more obvious spot to it. These models are pretty close. There's a good one. Okay, I'm going to take a look at this right here. We're in a standard cross section. We're going to go to annotate, cross section, minimum and maximum. We'll flip it to baseline 1, surface difference, and we'll look for a min max value. So when we apply, instantly it finds the min max values, and take a look right here. It shows me what the min and max values are of these points. 0.032, I went above it. If I zoom way in, just a little bit's all that was. So it's really neat, extremely fast tool to find the highs and lows in the flattened profile. Now let me say this, if you wanted to use classical end area, of course you can do it because it's in a cross section. Alright, back to PowerPoint for a moment. Locate critical points. We're at the end of the show here almost. We're going to look at how we can manually, this is the really neat thing, this is what brings it back to the game. Manually locate critical areas when transformed with the transformed tunnel surface. So we can come in, define perimeters of problem areas, and then isolate critical points within the perimeters. These points then are going to be transformed back to real-world coordinates so they can be uploaded to data collectors for real-world stakeout in the tunnel. This is what's neat. Let me step over here again. Okay, let's fit this. As it's doing that, I'm going to flip back over here for a minute. What we're going to cover is how we can take the critical points computed from this different stuff, like I said, and just send it back. So all we have to do is grab these models, look at them, and then we'll send it back. Once we get there, there we go. I'm going to take the difference, and I can run it against the zero or a correction, any one of the above. In fact, before I do that, what I need to do this right, and see the fit works there. Let's zoom out a little bit, delete everything. Okay, what you want to do when you do this quickly is you go to surface, view surface, perimeter on your differences. Apply it, fit it, and really you should run the depression check. I'm going to run that one more time because I want to use these surfaces. And I'm going to call that one depression and that one correction. Okay, and we've got those. Now once I've got that, what I want to be able to do is I'm going to come over here now to surface. I've displayed the difference, and I'm going to display the features inside correction, and I want just the critical points. So there they are. I can use the correction surface, or let me back that up. If I wanted to, I can use the depression surface with just the critical points. And they're just about the same. The ratio and the elevation give me about the same thing. So I'm going to use these combinations. I'm going to use the correction model, and I can see in here areas I've got a problem. Let me zoom in for a moment. We'll look at the way this works. Right here, for example, I need some work. So I'm going to come over here now for a moment, and I'm going to say use the differences surface. This is going to transform it back to the right coordinate system. But take depression as the difference value for the Z. This is what needs to be done. When I hit apply, it says identify first range point. I'm going to come out here and just put a perimeter around this thing like this. Okay, and when I reset once, then it's going to say identify key points or critical. There's one, there's one, there's one, and it could have been based on contours, whatever. Reset, And then what we have right there, in a nutshell, we've gone from a relative coordinate system right here back to a real world coordinate system, and there are the corrections that need to be applied to those points that we identified. So you can go back and forth and append data to this and very quickly put some really neat stuff together, and then go straight back to your collector and stake it in the tunnel, in the true 3D space. So now, in conclusion, you can see how you can use the in-rail tunneling tools to streamline your computer-aided engineering workflow when working with tunnels and enclosed shapes. And this is the end of today's in-rail XM edition tunneling.